Hey, hi, this is Joel over here, and this is the first video of our NLP course. And NLP, in the sense, it's called Natural Language Processing. So, what is natural language processing? We have to process the natural language which we, the humans, speak, and we have to make the computers to understand the language which humans speaking. Basically, computers understands zeros and ones, and we have to make computers understands the language which we speak into zeros and ones and make them to interpret and compute and gives us a proper results. So natural language refers to how people communicate with one another, and humans regularly communicate in many different languages like English or any other regional languages. So those languages should be converted into ones and zeros such that computers can understand and they can react intelligently to communicate to the humans. So this is called the overview of natural language processing. Natural language processing is a subset of artificial intelligence that enables machines to understand and communicate natural language like humans does. It also involves using algorithms and techniques such as machine learning, deep learning, and text analytics to interpret and analyze natural language content from audio recordings, document, images, or other sources. And applications of natural language processing. So natural language processing, so NLP can be used for sentiment analysis, chatbots, online searches, document analysis, smart assistants, and automatic summarization. And there are various kinds of applications for NLP. Let's see like one by one in later. And Google Translation is also one kind of NLP application. Microsoft Copilot, Bing in NLP, and all these are like kind of major applications that we are using in day-to-day life with NLP. Computational linguistics. So, what exactly is computational linguistics? It is the field at the intersection of language and computer science. In simpler terms, it's all about teaching computers to understand, interpret, and even generate human languages. It combines linguistic theory with machine learning and programming to create tools like chatbots, speech recognition system, language translators, virtual assistants like Siri or Alexa, and even grammar checkers like Grammarly. It's the brain power behind how machines make sense of human and communicate. So why it matters? Computational linguistics helps solve real world problems like breaking language barriers, enabling voice to text technology, and even analyzing social media trends. It's also key in developing natural language processing, which lets AI system reads and responds like humans does. Without computational linguistics, modern AI would have no clue what we are saying or typing. And history of NLP. So NLP is basically got generated in 1950 by a famous person called Alan Turing. And the first article for NLP has been titled called Intelligence, and which has been proposed now called as Turing test. And based on the famous experiment, which is like Georgetown experiment, which happened in 1954, it fully involved in automating translations of more than 60 Russian sentences into English. And in 1980s, most of the NLP systems were being based on complex sets of handwritten rules, which doesn't have any deep learning or machine learning. It's full of handwritten rules. And in 2010, deep neural network has been initiated and machine learning methods became widespread in natural language processing. And this is a short history of NLP. Let's understand the processing stages in NLP. We have 7 processing stages in NLP, and they are phonological analysis, lexical analysis, syntactic analysis, semantic analysis, discourse integration, pragmatic analysis. So let's go one by one. What is phonological analysis? This is all about sounds. When we speak, we produce various sounds like phonemes. Phonological analysis is used especially in speech recognition system, like when you ask your phone to call someone or search something using voice. Here, the computer breaks down your speech into phonemes and tries to understand how those sounds combine to form words. So basically, it answers what sounds did the person just make. And the second is morphological, or you can say it is as lexical analysis. So morphological analysis, which is also called as lexical because it step focuses on structure of words. It splits sentence into individual words, identifies the root forms and checks for morphemes and the smallest units of meaning in a language. For example, the word unbelievable has three morphemes, which is un, believe, and able. At this stage, the system also looks up words in the lexicon or vocabulary to see if they are valid. It's like asking, is this a real word? What does it mean? What part of speech is it? So these aspects comes under the topic called morphological or lexical analysis. And the third we have syntactic analysis. So syntactic analysis is also called parsing. This stage checks the grammar of the sentence. It builds a tree-like structure to show how words relate to each other. For example, in the sentence, the cat sat on the mat. The system identifies the subject, the cat, the verb sat, and the object on the mat. If something is grammatically incorrect, like sat the cat mat on, the syntactic analysis would flag it as a problem. It's all about making sure that sentence structure is correct. Semantic analysis. So now the system understands the words and the grammars. It tries to understand the meaning behind the sentence. Semantic analysis looks at the context and relationships between the words. For example, she unlocked the door with a key. It understands that the key is a tool used to unlock something. It also detects ambiguity, like a sentence which we say, I saw the man with the telescope. Did I see the man using a telescope? Or did the man have a telescope? Semantic analysis helps to figure that sometimes with the help of the next step, which is discourse integration. This is where the machine looks beyond just one sentence. It considers context across multiple sentences to maintain coherence. For example, John went to the store. He bought some apples. Discourse integration helps the system understand that he refers to John. This step is essential for chatbots, personal assistants, and language models to carry on meaningful multi-tone conversations. Finally, we have pragmatic analysis. This step focuses on the intent behind the words because sometimes the literal meaning isn't enough. For example, if someone says, can you open the window? They are probably not asking if you are physically capable. They are politely asking you to open it. Pragmatic analysis understands these tone, sarcasm, commands, and even hidden meanings based on the situation. It answers what does the speakers really mean. This is especially important for AI systems to interpret human emotions, politeness, commands, and real world knowledge. So, in summary, phonological analysis is used for recognizing sounds, lexical analysis, identifying words and meanings, syntactic analysis, checking grammar structure, semantic analysis, understanding the meaning, discourse integration, maintaining context across sentences, and pragmatic analysis, interpreting intent and implied meaning. Each step builds on the previous one, forming the backbone of how machines understand human language. So next time you talk to Siri or Alexa, just remember they are running through all these steps in milliseconds to reply to you. Now we are going to talk about computational linguistics. So what is computational linguistics? Computational linguistics is a branch of linguistics that uses computer science and algorithms to analyze and understand human language. It's the science behind how machines read, interpret, and generate natural language. Unlike programming languages, which are clear and unambiguous, natural language is messy. For example, the word bat can mean a flying mammal or a sports equipment. This is called lexical ambiguity. One core goal of computational linguistics is to resolve this ambiguity so that machines can understand what we really mean. Let's talk more about ambiguity because it's the biggest challenge in language processing. Let's consider the sentence: I saw the man on the hill with a telescope. Now, did you see the man using a telescope, or was the man on the hill holding a telescope? This kind of structural and semantic ambiguity makes it hard for machines to interpret meaning unless we teach them to disambiguate. That's it. To figure out the correct meaning from the context. Natural versus programming languages. Programming languages like Python or Java are precious and have strict rules. Every command has only one meaning. Natural languages like English are ambiguous, flexible, and filled with exceptions. Computational linguistics helps bridge this gap by creating algorithms that can understand human-like language in a structured, computer-friendly way. Levels of ambiguity. We have four levels, which is lexical ambiguity, syntactic ambiguity, semantic ambiguity, and pragmatic ambiguity. Lexical ambiguity. Let's consider the sentence: the fisherman went to the bank. Is it a river bank or a financial bank? Ambiguity exists over here. Syntactic ambiguity. Visiting relatives can be boring. Are you visiting them or they are visiting you? So syntactic ambiguity exists over here. Semantic ambiguity. The teacher said on Friday she would give a test. Did she say it on Friday or is the test is on Friday? Again, ambiguity exists over here. Pragmatic ambiguity. Can you pass the salt? It's not a question about ability, it's a polite request. So, resolving these ambiguities is key to making NLP systems more accurate. NLP tasks and what computers needs to know. To process language, an NLP system must understand phonology, morphology, syntax, semantics, pragmatics. As I said earlier, phonology is the sounds of speech, morphology is the structure of words, syntax is the grammar and sentence structure, semantics is the meaning, pragmatics is the context and intention. Computers need to integrate all these layers just like humans do when we speak or read. Empirical laws and word frequencies. Here where computational linguistics gets mathematical. You ever heard of Heaps Law? It says that in any large text, the most common word appears twice as often as the second most common, three times as often as the third, and so on. For example, in the Mark Twain's Tom Sawyer's, words like the and of occur far more often than content heavy words like fence or paint. This tells us a lot about language patterns and helps NLP system prioritize important words. Content words versus function words. Let's break language down into two parts: content words and function words. What are content words? Nouns, verbs, adjectives. These carry meaning. Example: Daddy play ball. Even with minimal grammar, the meaning is clear. And for function words, prepositions, conjunctions, articles, they hold the sentence together but don't carry much meaning alone. Computational linguistics often filter out functions words during processing to focus on the key content. Type versus token. Here's the fun concept where TTR, which means type token ratio. Tokens are total number of words, types are unique words. Let's consider the sentence. The quick brown fox jumps over the lazy dog. The dog barked loudly. So tokens, there are 13 total words, which is the quick brown fox jumps over the lazy dog. The dog barked loudly. So there are 13 total words, and the unique words are the quick brown fox jumps over lazy dog bark loudly. So there are 10 total words. So 10 divided by 13, it's approximately 0.769. So the final TTR value is 0.769. A higher TTR means more diverse vocabulary. A lower TTR means more repetition. This is a super helpful in analyzing speech patterns, language learning, or even writing style. And real world applications. So where is it computational linguistics are being used today? Chatbots like ChatGPT, voice assistants like Alexa and Google Assistants, translation tools like Google Translate, grammar checkers like Grammarly, search engines like Sentiment Analysis, and more. Let's begin with Heaps Law, an important statistical observation in language processing. So what is Heaps Law? It tells us that as number of words in the document increases, the number of unique words also increases, but at slower rate. It is expressed as V of n is equal to k into n power beta, where V of n is the number of unique words, n is the total number of words, k is the constant, usually around 10 to 100, and beta is the value between 0 and 1, typically between 0.4 and 0.6 for English. In simpler terms, the more you write, the more unique words you will use. But after a point, new words show up less frequently. Most of our vocabulary is made of repeated common words. So let's consider an example of Heaps Law numerical. So here they have given a vocabulary growth of Jane Austen novel. So it has total words which is n and distinct words which is v of n. And total words are 10,000, 50,000, and 1 lakh. And distinct words are 2,000, 5,000, and 8,000. So as a first step, we have to find log of n and log of v of n. So log of 10,000 is like 4, and log of 50,000 is 4.7, and log of 1 lakh is 5, and log of v of n is 3.3, 3.7, and 3.9. So once this log transformation has been done, step 2, we have to calculate the slope, which is beta. As we know, log of v of n is equal to beta into log of n plus log of k. And the formula for beta is equal to n into summation of log n into log of v of n minus summation of log n into summation of log v of n divided by n into summation of log n square minus summation of log n the whole square. So the values have been substituted over here and we found beta is equal to 0.595. Now it's time to calculate the intercept, which is log of k. So log of k is equal to summation of log of v of n minus beta into summation of log n divided by capital N. So capital N is the total number of rows that exist in the numerical table, and we have 3 over here. So all the values has been substituted, which is 10.9 minus 0.595 into 13.7, which we get approximately 0.916. So K is equal to approximately 2.5. Inferences from Heaps Law. Here are some key insights from Heaps Law. Vocabulary growth, language complexity, empirical fit, K as a scaling factor. Vocabulary growth. New words keep coming but slower over time. Language complexity. Natural language has a lot of repetition. Common words dominate, but occasionally unique words still add richness. Empirical fit. Most English texts fit well within Heaps' expected beta range of zero point 0.4 to zero point 0.6. K as a scaling factor. Higher K means more unique words early on in the text, useful to compare authors or genres. So, applications of Heaps Law. So, where is Heaps Law being used? It's been used in linguistics to study vocabulary richness and compare different text or writers. Search engines like helps optimize indexing and estimate storage needs. Text analysis like editors and researchers use it to evaluate writing style and content complexity. It is a powerful tool that helps both machines and humans understand the richness of language. Turing test. Now let's switch gears to one of the most iconic concepts in the AI, that is the Turing test, the named after Alan Turing. The Turing test is a benchmark used to test machine intelligence. So how it works? A human judge chats with two participants. One is machine, the other is human. The communication is text only with no visuals or audio cases. If the judge can't reliably tell which is machine, the machine is said to have passed the Turing test. That's huge. It means the machine has shown human-like intelligence, at least in conversations. But passing the test is not easy. To succeed, the machine must understand natural language, reason logically, use contextual knowledge, respond like a person. Think of smart chatbots, AI companions, and virtual assistants. They are all trying to get closer to passing this test. Even today, the Turing test remains a symbol of intelligent behavior in machines. But some AI systems come close, very few can consistently fool a human judge. It's not just about grammar, it's about understanding emotions, context, and intent. So that's it. This is the end of our first module in NLP, which is natural language processing. Hope you guys understood well. Thank you. Hey guys, in this video, we will just solve a numerical based on minimum edit distance. So before starting into numerical, let's see the value cost for insertion, deletion, and replace. For insertion, we have 1 as a edit value cost, and for deletion, we have again 1 as an edit value cost, and for replace, we have 2 as an edit value cost. So now let's consider two words, which is cot, C-O-T, and cat, C-A-T. Cot is being written in column wise and cat is being written in row wise. And let's start solving these two words for finding the minimum edit distance. As a first step, we have to create a minimum edit distance table, and it has hash value in the starting and of cot and cat words. So first step, you have to fill the first row and column with 0, 1, 2, 3 up to n words, and same as way for cat also, which is like 0, 1, 2, 3 up to n letters. So now remaining cells has to be filled to find out the minimum edit cost. So now let's see. As a first step, we are just considering C over in the row and C over in the column. As the first letters are C and C, since these letters are same, we will consider the same diagonal value over here, which is 0. So this 0 has been written over here, and It doesn't have any computational functions over here, just the diagonal value is being written over there. Now this C is being compared to the letter O. Now C and O are two different letters. If both the letters are different and the diagonal values, you have to be omitted. So now to fill this value, you have 0 and 2. So from 0 and 2, the minimum value should be taken, which is 0, and 0 should be summed with 1. So now the answer of 0 plus 1 is 1, which has been written over here. Now let's compare the letter C with T. Again, C and T are two different letters. So diagonal value, which is 2, is being omitted over here. And from 1 and 3, you have to pick the minimum value, which is 1. And this 1 should be summed up with 1. So as a result, you will get 2. And this has to be substituted over here. So we have filled the values of 0. Now we will just move on to the values of A row. So now A is being compared to letter C. And of course, A and C are two different letters. So as the same way, this 1 is being omitted. And from this 2 and 0, the 0 is the minimum value and plus 1 should be done with the 0. And as a result, you will get 1 over here. Now let's consider A with O. So again, A and O are two different letters. So this diagonal value 0 is being omitted. And from this 1 and 1, the minimum value 1 is being taken and it's been summed up with 1. As a result, you'll get 2, which is being given over here. So now A and T. So again, it's a different. So diagonal is being omitted and 2 is being taken, which is minimum, and plus 1 is being done. And as a result, 3 is been given over here. Now let's see the last row, which is T, and let's compare T with C over here. So T and C are different letters, so diagonal is been omitted and 1 and 3 is been taken. So let's erase this. So 2 is been omitted and 1 and 3 is been considered. And from 1 and 3, the 1 is the minimum. So 1 plus 1 is been done. Sorry. 1 plus 1 is been done. And as a result, you'll get 2, which has been stored over here. Now, T and O are been considered. And same, the diagonal is being discarded. And from 2 and 2, the minimum is been taken, which is 2. And plus 1 is been did. And you will get 3 as an answer. So now if you see over here, T and T are been same over here. So since it's same, as we did earlier over here for C and C, let's erase this. Yeah. Since in earlier for C and C, we just took the diagonal values, right? Which is 0 over here. So same way for T and T, you have to just pick this diagonal value 2 over here. So now 2 is being stored over here. And the last cell value is being considered as the edit cost over here. So the edit cost of cot and cat is 2. Let's verify this. So we have two words, right? Cat and cot. And as you can see, C and C both are being equal over here. And T and T are being equal over here. But A and O are not equal over here. So A and O should be replaced. So A and O should be replaced. And as earlier, if you check, for replace, we have the cost value as 2 over here, which is like default value. And now the same 2 is being got over here in edit distance table. So the edit cost for this, I mean the replace cost for A and O is 2 over here. So this is being verified that our edit distance value which we got through the edit distance table is proper and correct. And yeah, that's it of minimum edit distance numerical. Hope you guys understood. See you later. Thank you. So hello everyone, this is Joel over here. And in this video, we will be solving a numerical based on n-grams. And yeah, let's start to solve this. So we have a question with a training data set over here. And this is the question which has been provided over here. And we have to solve a unigram and bigram. And we have to find the n-grams for this targeted sentence over here. So basically, our motive is to find the bigram value of this targeted sentence using the training data set over here. So here in the training data set, you have 4 sentences with starting of sentence with s and ending of sentence with slashes. And as a first step, all these words should be counted, including these s and closing tag of s. So total number of words or tokens, you can say we have 30 over here. So 30 over here we have. And as a first step for unigrams, we have to count the total number of words that exist in a training dataset. So you can see S exists for 4 times and I exists for 5 times and no exists for 1 time and who exists for 1 time. So basically the total number of times occurring of each word should be counted and listed as a second column of the table. And as a third column, since we got 30 as a total tokens, right? So we have to divide the count divided by total number of tokens over here. So 4 by 30, you got approximately 0.133 and 5 by 30 is like 0.1667. And same way, all this P of W is being found over here. Now, our targeted sentence is like S, I would like to help slash S. So to find the bigram for this, we have to pick 2 words recursively for checking the bigrams. Unigram is a single word and bigram is like 2 words you can say. And so here S and I is been considered. So the count of I is 3 and the count of S is equal to 4. So P of I and with S. S is like kind of empty statement you can say, or else like starting statement. So P of I with S is like 3 by 4. You got 0.75 over here. And second we have I and would. So would occurs for 1 time and I occurs for 5 times, which is would and I both are occurred together is 1 time, but I alone like got counted is like 5 times. So what I'm trying to say is in first sentence I along with S is occurred for 3 times and S alone occurred for 4 times. So same way in the second row, so would and I together is occurred as 1 time, but I alone occurred as 5 times over here. So 1 by 5 is 0.2 we have over here. So next, would and like. So would and like is been taken and the count of would and like occurred together is 1 time and would alone occurred is 1 time. So you have 1 by 1 which is 1 over here. And like and 2 occurred together is 1 time and like alone is occurred is 1 time. So 2 like is nothing but 1 over here. and 2 help, it's 1 and 2 is 3. So you got 1 by 3 and it's like 0.333, and help of S, you get it as one time, like help and closing tag of S occurred for one time and help alone occurred for one time in the training data set. So P of uh, closing tag of S and help is like 1 by 1, which is 1 we have. So all these values should be multiplied, and so if multiplication happens, you'll get the probability of this particular targeted sentence over here. So probability of I would like to help is 0.75 into 0.2 into 0.1 into 1 and into 0.333 and into 1. So as a result, you will get 0.499 something, and we will just round it off to 0.05 over here. So that's it, guys. So basically ngrams is, they will be providing you a training data set, and as a first step you have to count the total number of words or tokens, and using that we have to find a unigram. And as for bigram, a targeted sentence will be provided, and you should pick two words from a sentence, and you have to find the probability and multiply all these things to get the bigram count of your targeted sentence. So the general formula over here is probability of word 1, word 2, word 3 up to word n is equal to probability of word 2 over word 1 into probability of word 3 in over word 2, and it goes on up to n words. So yeah, that's it, guys, for ngrams, and see you on another video. Stay tuned. Thank you. Hello guys, welcome to another video of our NLP series. So in this video we will be solving a numerical based on Laplace smoothing. So let's start solving this. So here they have provided a question over here which says that given the bigram counts of table 1, so this is the table 1 over here. It is a bigram count of corpus or training data set, you can say, and the frequency of words is listed in table 2. So this is table 2, which is like frequency of words or count of words, you can say, from the corpus of 9332 sentences. So the corpus contains 9332 sentences, and the vocabulary size of the corpus is 1446, which is, you can say, unique number of words over here. So they have provided two target sentence over here, which is S tag I want English food now and closing of S tag, and S tag I want Chinese food now and closing of S tag. So, and they're also provided like add k smoothing where k is equal to 0.5. So 0.5 smoothing should be applied over here, and they have also gave some assumes over here, which is uh, S and I occurred for 1230 times, and want and English together occurred for 155 times, and English food occurred for 0 times, and food now occurred for 0 times. So we will see this while solving the numerical over here. So let's solve this. So before solving, let's look into a general formula over here. So probability of adding k, which is like Laplace smoothing, word y I to word I minus 1, we have formula as C of word I minus 1 comma word I plus k divided by word I minus 1 plus k into v. V is nothing but vocabulary size, you can say, which is 1446, which is given over here, and k is nothing but 0.5, and even k is been also provided from the question. So as a target statement, first we have I want English food now. So let's create a table over here, and first column is bigram and bigram count, word frequency, and smoothing probability. So first sentence is I want, so I with starting sentence, right? S tag we have, right? So S tag and I is been taken, and bigram count of S tag is So the bigram count of S tag is 1230, which is like S and I occurred for 1230 times. So that has been entered over here. And the word frequency of S is 9332 because all the sentence will have an S tag. And from the question, you can see the corpus contains 9332 sentences, right? So which means we have 9332 sentences has S tag over here. So the word frequency of S tag is 9332. So as a formula we are substituting this bigram count value, which is 1230, plus smoothing it, right? So K value is 0.5 by word frequency is 9332 plus K value is 0.5 into 1446. 1446 is the vocabulary size which has been provided over here. So once all this been applied and computed, you will get 0.122377 as your smoothing probability. So now let's try for row 2. And from a targeted sentence, our next two pair of words is I want. So I and want has been written over here. And what is the bigram count of I and want is? And they didn't provide in the question. So you have to look into table 1. So I and want, right? So the count is 8 to 7. So the bigram count is 8 to 7. And the word frequency of I is 2435. So this 2435 has been written over here, and these values has been substituted in the formula, which is like bigram count is 827 plus K value is 0.5 divided by, and you have the word frequency is like 2435 plus K value as 0.5 and V value as 1446. So once it get computed, you'll get 0.262033. So same way guys, same way all these rows has been done. And at last, if you multiply all these things, you'll get 5.568 into 10 to the power of minus 11. So this is our final answer after adding the smoothing value of 0.5 to this targeted sentence. So now let's see sentence 2 over here. So same way we have a sentence 2, which is I want Chinese food now. So as a first step, we will take the first two pairs of words, which is like open statement yes and I, and both occurs for 1230 times and I occurs for 9332 times, and we're just substituting in a formula which is 1230 plus 0.5, which is K value, divided by 9332, which is word frequency value, plus K value 0.5 into V value, which is 1446. So you will get 0.12237. So same procedures. So you will follow the same procedures over here, and at last all the values has been multiplied, and you will get the probability smoothing value is 4.107 into 10 to the power of minus 10. So that's it guys of Laplace smoothing. So basically in Laplace smoothing, they'll be giving you two tables and targeted sentence. As a first step, you have to find a bigram count and word frequency. And then from the question, you should identify the V value and I value, and just substitute in this formula and multiply all the answers. So you'll get the probability of sentence after Laplace smoothing. So yeah, that's it guys, and we'll see you on next video. Until then, stay tuned. Thank you. Hello everyone, this is Joel over here. So in this video, we will be solving a numerical called CYK algorithm from module 5. So we are just skipping module 4 since there is no much major numerical in module 4, and we'll be just solving CYK algorithm in this numerical. So in our question, they have given these production rules over here, and also the input string, which is called AABB. So our motive is to find whether this input string can be passed by with these production rules, whether this production rules is capable of passing this input string or not. That is our motive over here. So as a first step, we have to generate a table over here. And for generating the table, we have to check the length of the string. So length of the string is 4 over here. So we have to create 4 rows and 4 columns. So 1, 2, 3, 4. And as for second row, which is 1, 2, 3, and for third row, which is 1, 2, and at last you have one cell. So this is the method to create a table. And second step, you have to write all these strings over here, which is A, B, and B over here. So now here we have to check whether this A is being produced by any of these production rules over here. So you can see A is being produced by these rules over here, which is terminal of A. So this A is being written. So same way this A is also being produced by this terminal of A. So again A is being written over here. And for B, if you check, we have B and C over here. So B comma C, and same way for this B also B comma C we have. Now this row we have successfully found the values over here. Now let's move on to the second row over here. So second row is a combination of these two cells, you can say, which is A and A. And now for finding this, we have to do the cross product, which is A and A we have, right? So this we have to do it as a cross product, so we will get AA. So now we have to find from the production rules, is there any production rules producing this AA? So yeah, we have C over here producing this AA. So now let's write C over here. And now for second cell, it is the combinations of these two cells. So here we have A comma BC. So now we have to do the product over here, and we will get it as AB and AC. So we have to find whether any production rules are able to produce this AB and AC over here. So yeah, we have A producing AB and AC, right? And there is no any production rules producing AC. And as well as you can see, S is also been producing this AB over here. So AB is being produced by A and S. So S and A is being written over here. Now you have to check the combinations of these two to find the values of this particular cell. So we have BC and BC. So we might get it as BB, BC, CB, and CC over here. So for these rules, you can see BB is being produced by S, and it's also been produced by B. And for BC, if you check, there is no any rules producing BC. For CB, no. Even for CB, there is no. And for CC, we have A over here. So our production rules are producing SBA. So we will write it as SAB over here. Now we have done the second row also. Now we'll just move on to third row. So third row, we have to pick the combinations of C and SA over here. So we have C and AC, but we have to take it as a combinations of A, A, B. This AAB is the first three characters of a string, and we can write this AAB into two different forms, which is like AAB, which A is being separated, and as well as you can write it as AA separated by B. So now for A, if you check, we have A producing this A over here, which is this A, and for AB also, if you check, we have SA over here. So this SA. And now for AA, if we check, for AA, we have C producing over here, so C. And for B, we have B and C over here. So now cross product has been done for these two, which is AS, AA, and CB, EC. So now for AS, there is no any production rules producing AS. So you can see there is no any production rules producing for AS. And for AA, if we have C producing AA over here, and for this side, we have CB, CC, right? And there is no any production rules for CB. And for CC, we have A producing it. So now at last we have C and A. So C and A. So now for this particular cell, we have to take these two cells combinations, which is A, B, B. So I'll write it over here, A, B, B, A, B, B. So we have two combinations, which is like A and BB, or else like ABB and A B. So yeah, now we have to find the terminals or the production rules which is producing A. So A is been produced by A over here, right? So A and BB, and BB is been produced by SAB over here. So SAB. Now for AB, let's check. For AB, we have S and A, and for B, if we check, we have BC over here. So once we are doing a dot product over here, So we might get it as AF, AB, AA, and SB, SC, AB, AF. Sorry, AC. So now there is no any production rules producing AS over here, and even SB, SC, and AC. And AB is being produced with the production rule F. We can see F, and AA is being produced by with the production rule C over here, so C. And for AB we have A over here. So F, C, A we have. So F, A, C. I have written over here. So now last step is to find this particular cell over here. For finding this particular cell, we have to take the combinations of these two cells over here. And we have string AABB, right? So this AABB will be written into three forms. So the first form is AA and BB. Our second form is AAB and B. And the third form is A and ABB over here. So now you can see AA, right? So from the table, AA produces C over here, right? So this C is been written over here. And BB is been produced with FAB over here. So FBA. There is no any proper rules for writing SBA and SAB. You can write it as per your own and just jumble it. And yeah. So now for AAB, if we check, so AAB, right? So these three cells we have it as CA over here. So this CA is been written, and for B, which is we have BC over here. So BC, and for A we have A terminal now, and for ABB, so ABB we have FAC over here. FAC. So now we have to do the product over here. So we will get CS, CB, and CA, and in this side we will get it as CB, CC, and AB, AC. So here AS, AC, AA we will get it. So now you can see CS, CB, and CB, AC, AS, AC are these things and all been produced by our production rule over here. So now just check for CA. Now CA is being produced by B over here. So B, and for CC you can see it is being produced by A over here. So A, I mean for A, and for AB it is being produced by A and S, right? So A and S, and for AA it is in again produced by C over here. So at last we have S, A, B, C. So S, A, B, C. So now in a topmost cell, if we have F, then we can conclude that this particular string can be passed by the production rule. If the topmost cell contains S, then you can say it can be passed by the production rule. If there is no S, you can say that this production rule is not sufficient to pass this particular input string. But in our case, we got S, so we can say this production rule is capable of passing this particular string over here. So that's it, guys. This is the numerical of CYK algorithm. Hope it understood well. Thank you.